Hey, I'm Oleg, and I will present model-based reinforcement learning via Latent-Space Collocation, which is joint work with tuning. Current model-based reinforcement learning methods struggle on long-horizon tasks. Here's a tool-use task where the robot needs to pick up the stick and push the thermos with it. The CM shooting planner used in recent work, such as Visual Foresight or Planet, is not able to discover picking up the stick and converges to a poor trajectory. In optimal control, many methods have been proposed that can perform long-horizon behaviors. These methods are based on the idea of collocation, which optimizes a sequence of states instead of just actions. While collocation is known to perform better than shooting, it's unclear how to scale it to learned visual models. As images are high-dimensional and non-Markovian, optimizing a sequence of images is particularly challenging. We propose to handle this problem by performing collocation in learned compact latent space. Specifically, we address the setting of visual model-based RL. We plan from image observations and learn to encode them into a latent state. We also learn the latent dynamics model and the reward predictor that defines the task. Shooting methods sample action trajectories and enroll them into the future using the predictor model. Using the reward model, shooting directly optimizes the actions for maximum reward. Shooting suffers in performance as it requires recursive application of the model, which makes the optimization poorly conditioned. Intuitively, because the effects of actions compound significantly over time and affect the entire future trajectory, optimizing actions directly is challenging. Instead of just optimizing actions, we propose to optimize a sequence of future latent states and ensure that the plan is feasible using collocation. Collocation optimizes the states to achieve a high reward while ensuring that the sequence conforms to the model dynamics using constraint optimization. A sequence of actions is also recovered by optimizing the dynamics constraint. We use dual descent on the Lagrangian and the Levenberg-Marquardt optimizer to solve this constraint optimization problem. This summarizes our proposed visual model-based RL agent. Since the optimization is performed in the latent space of a learned dynamics model, we call this agent latent collocation, or LATCO. In contrast to shooting, because it optimizes a sequence of states as well as actions, LATCO can anneal the dynamics constraint in the beginning of the optimization, which allows it to quickly discover the states with high reward and escape the local minima that we saw earlier. Let's see how annealing can help on our thermos task. Collocation quickly finds the high reward region in the very beginning, constructing plans where the stick flies in the air by itself. As we enforce the dynamics constraint, LATCO fine-tunes this initial trajectory to satisfy the dynamics, eventually converging to a feasible trajectory. Here are more examples of LATCO plans on the thermos task, as well as the long horizon hammer task and a pushing task. These multi-stage tasks are challenging as the planner needs to discover all stages necessary to complete the task only from a sparse binary reward, instead of relying on a shaped reward or demonstrations that would provide a dense signal. LATCO is consistently able to solve such long horizon tasks using latent state optimization, while shooting fails. To empirically confirm the benefits of latent state optimization, we evaluate LATCO in a visual model-based reinforcement learning setting. We consider these 7 robotic manipulation tasks with sparse rewards. The first 5 tasks use online data collection only, and the agent explores to learn the model from scratch. For the thermos and hammer tasks, we use an offline dataset with online fine-tuning to overcome the exploration challenge. We further show the visual plans created by our agent. Note that these are not real images, but predictions from the model. LATCO creates effective plans and is able to execute them. Quantitatively, our agent performs well on many of the tasks and can even solve the hardest tasks in the suite. We evaluate our agent against prior work on model-based development use shooting methods, such as Planet, which uses CM, MVPI, which is another sampling-based shooting method, and optimizing actions with gradient descent. Shooting methods can solve the dense reward versions of these tasks, but fail when only a sparse reward is available as shown in this plot. Shooting rarely succeeds even on the simple tasks, and fails completely on the challenging hammer and thermos tasks. In the paper, we further derive our method from a probabilistic perspective and show that it works well for planning under uncertainty. In summary, we found that optimizing a sequence of future latent states allows better planning than previous works that optimize actions directly. Using constraint optimization, we designed a principal method for optimizing states that solves multi-stage tasks from images, and a probabilistic Gaussian version of LATCO performs effective planning under uncertainty. Check out our paper for derivations, DeepMind control suite results, and additional analysis and ablations, our website for additional videos, and our GitHub for the open source code.